today we will learn fixed plane analysis. Okay. Before that, since yesterday we started discussing on bifurcation. What was bifurcation? That is what we learned.
Qualitative change in parameters versus qualitative change in
It's a quantitative change in a parameter that may lead to a qualitative change in the stability property of the system, I mean of the equilibrium points, and also in sometimes you may find that is for one set of values, or maybe for the new positive interval there is only one equilibrium point, but for other interval, I mean for negative values, there will be more than one equilibrium point. That can also happen. Okay, so that example I am now going to give you, because otherwise you will find that is okay, because we have yesterday we have seen one example. Through that we understood what is bifurcation, but another type of example unless I give you, then it will remain incomplete. In that connection, a few times we talked about Duffin equation. What is that? A nonlinear. It represents a nonlinear spin mass damper system. You can also take a nonlinear RLC. Okay, anyone. Here's the example. Spring mass, a nonlinear spring mass damper system, or you can also nonlinear RLC. How does it look like? X dot plus C into Y dot plus alpha Y plus beta Y cube equals to F. Here generally we write K. Isn't it? This one sometimes we write C, sometimes we write D, whatever, right? If you compare this with the linear one, what is then that? That is M Y double dot plus C Y dot plus K Y equals to F, right? This is the linear spring mass damper system. Just to compare, we also learned about Van der Pol equation. Why I am just writing all these equations again and again? Because this is for the first time we are learning nonlinear. So if we repeatedly hear the same thing and if we repeatedly see the same thing, then gradually it will get stored in our memory. That is the reason, that is why I am just keep on repeating the same thing in a different way. Okay. What was the Van der Pol equation? What we learned? M y dot, you can write M or it may not be M, and then we wrote 2C into epsilon square minus 1, or what did I get?
I square minus 1.
Right, sorry. Y square minus 1 into y dot, right? Plus ky equals to F. This you can talk about here. The damper is nonlinear. However, the spring is linear, right? This is the dashpot term, that is nonlinear, and the spring is linear. No doubt about it. If it is LTI, all of them are linear, absolutely, that is why we are quite familiar with. Now Duffing equation. Duffing equation means this is the general term of equation, that is where you see at this moment what happens, that is the spring. This kind of spring is called hardening effect of spring. That is not only carrying 2y, but now the force given exerted by the spring, that is all, another component is there which is proportional to the cube of the displacement. Okay, in general the force exerted by a spring, that proportional to displacement, right? You know, that gives us k into y. If at the same time I say that is it is proportional to y also, y cube, then what will happen? There is some constant k into y plus another constant into y cube. That is the situation here. After this, somewhat later, we will learn the equation type of a robotic manipulator, maybe that of a drone or a underwater vehicles. That will also have a specific form, which is called Euler-Lagrange equation. That is, at this moment, you see still it is like, what should I say? That is still it is manageable. Why? Because the coefficients, they are first of all separate, and also that is the coefficient, they are fixed. Now you see, compared to this one here, what is happening? They are in both the cases constant coefficients, right? Here that is m, c, k, all are constant. Here also, that is here also you can write m or may not be, c, k, b, all are constant. Okay, but now here you have the damping term, that is which is state dependent, right? So similarly, that is if you see the expression or the governing equation of a robotic manipulator or a ground robot or a UAV or underwater vehicle, that is highly nonlinear. What kind of nonlinearities? Some kind of of course, the coupling between the states and coupling between the state and the input, they will definitely be there. In addition, like some of the higher order nonlinearity, square or cube, then nonlinear drag, all those kind of things will be there. At this moment I am not introducing, later I will show you. Why I am introducing all of them? So that is you get a complete feeling about that why should you learn nonlinear control, or especially nonlinear system analysis, because at the very beginning I told you that, or even that is I posed the question to all of you, that what is the requirement for learning nonlinear control or nonlinear system analysis. If we see that is, oh, there are many systems around us which are genuinely nonlinear, and if we don't learn nonlinear system analysis, then definitely that is we will be in a void kind of situation where we don't have the power or the tools required to analyze nonlinear systems. So that's why that is simultaneously we are learning the nonlinear system analysis, and then that is like quite a bit often it is I'm giving you different real world examples which are typically nonlinear, and then what are the different type of nonlinearities. Okay, so then a particular case is that here we have the damping term, c greater than 0, it is a damping term. Okay, now what will be the undamped version of the Duffing equation? You might think that is why I am thinking about considering the undamped Duffing equation. It has a particular purpose, it will be evident very soon. So what should I write? That is y double dot plus ky plus beta y cube equals to f, right? Why I have done this? I am taking the force to be identically 0. What is the purpose? We are planning to analyze the behavior of the unforced system. Behavior of the unforced system means actually we are thinking of finding the equilibrium points. Okay, that is our main notion. So if it is 0, and first of all, that is what is the state variable representation? If I write it is x1, y is the first state, and then x2, that is the velocity, or even y dot, that is the second state, then what will be my state variable? So x1 dot equals to x2, and then x2 dot equals to, what should I write?
Minus k1 minus.
I consider k equals to 1 just to keep one parameter. Okay, you can keep k, not a problem. But just to keep one parameter, because ultimately this will give rise to a kind of bifurcation. So thinking that at this moment I don't want to handle, I don't want to be dependent on two variables or two constants. So that's why I am considering only one. So x2 dot equals to minus x1 minus beta x1 q plus u, right? If it is unforced, then of course it will be 0. Is it fine? If anyone has any problem, feel free to ask. Now suppose the first one I am denoting by f1 of x, and the second one that I am denoting by f2 of x. Now how to find equilibrium points? They are the solutions to the f of f1 of x equals to 0 and f2 of x equals to 0, right? Solution to f1 of x equals to 0, that yesterday I used the identical equals to that sign, and f2 that is also identical equals to 0. Then from that, what will you get? Right? So x2 star equals to 0. That means whatever may be the equilibrium point, its x2 coordinate will always be 0. Kashi, any problem regarding the notation? I wanted to write that this is the input term, but as we are now analyzing the behavior of the unforced system, so that's why eventually it will be 0. That means this term won't be there. And this function, I have just named this as f2, this is f1. Okay? And then how to find out the equilibrium points, that is individually, not like that, it will be the solution to these two equations, right? So x2 star will be 0, and what will be the another one? x1 star plus beta x1 star cube equals to 0. Isn't it? If I make any mistake, please tell me. Then x1 star right? Then what would be the solution? At this moment, I didn't write plus minus root over. There is a reason. You might think that is, I could have directly written, either I could have written plus minus root over 1 by beta, or even that is plus minus I root over 1 by beta, right? But at this moment, since I didn't specify the range of beta, I didn't write anything. If you consider the beta If you consider the beta positive, then there will be something. If beta is negative, then also there will be something. Now that we will analyze. Okay. Here at this moment, that is the Duffing equation, that is fine. Here when we are talking about this, then k is of course greater than 0 and beta is not equals to 0. Okay, you might say that is, sir, if it is a spring mass damper system or something like that, then definitely beta would be positive. Okay. Now for the analysis purpose, let's see that is if that is negative, then what happens?
But always the displacement should be a real number, right? Then how can be x1 star is in the imaginary plane?
Let's see. So that's why I didn't write it. You are right. That is here. That is we are like thinking about the solution, right? So here my equilibrium points. That means x1 star, x2 star. This is my equilibrium points. I have to find the equilibrium points, right? So then, that is first of all, like let's see what happens if beta positive and if beta negative. Okay, so if beta greater than 0 versus beta less than 0. Can you please tell me that is what happens in that case? Remember one thing, that is this is where there is nonlinear differential equation, right? But in this case, that is we cannot expect an imaginary solution. The solution should be real, okay? So that's why accordingly you have to think. So here what is like x1 star equals to 0. So that is for sure. So for beta greater than 0, one possibility is 0, 0. Now we have to see whether any valid equilibrium point exists under this category. Once again, for beta greater than 0, this is this one, that is x1 star equals to 0, this doesn't depend on the beta, right? So whether beta greater than 0 or less than 0, this 0, 0 equilibrium point, this is a common candidate. Now whether there exists any other, that we have to think. Okay. Now see, that is you come to this equation 1 plus beta x1 star equals to 0. If beta is positive, then that is what solution it will give you. Then x1 star, that will be plus minus
I1 by beta.
this one. But as I said, that is here we cannot expect an imaginary solution, right? So that is if beta greater than 0, we have only one equilibrium point, 0, 0. Now what happens if beta less than 0? Then plus minus root over 1 by beta, right? So now have you seen, if beta is the parameter, then in the whole positive range you have only one equilibrium point, 0, 0. Now if it crosses its boundary, that means from positive to negative at beta equals to 0, there we cannot directly because if beta equals to 0, then it is completely linear spring mass damper system, which behavior is like pretty simple. It would be sustained oscillation, we do not have any confusion regarding that. But now that is bifurcation means that is if the range of the parameter changes, then there can be some abrupt effect in the system, right? That is my bifurcation. So what is happened, that is beta, that is it is greater than 0. From that, if it migrates into the region less than 0, that means from positive side, if it goes to the negative side, then you see that is one equilibrium point. Earlier it was only one equilibrium point, now it will give rise to 3 equilibrium points. Not only that, later we will analyze the stability. That too you will see, that is for this one maybe this is stable, but for this one maybe it would be unstable. Or maybe the other one we are not sure about what will be the stability property. But today we are not going in that direction because otherwise I cannot even start with the Theosporian analysis. But in the yesterday's example, what we learned, that is for that change in the parameter, the stability property of the system that changed, right? And today what did we learn? That is again a quantitative change in the parameter will lead to, that is more than one, or even that is will lead to a different number of equilibrium points, right? A change in the number of equilibrium points. So bifurcation means that is these two effects can happen, either separately or even that is simultaneously. One is that is change in the stability property of the equilibrium point. Like yesterday you have seen, that is one of the equilibrium point, it was stable for the positive range of the parameter. The same equilibrium points became unstable for the other range of the equilibrium, for the other range of the parameter, right? Here also you will see the similar one. But in addition, these two are the new equilibrium points which do not exist if the parameter is in the positive interval, right? So these two are the main effect of bifurcation. And what is the point of bifurcation? That the zero value of the parameter, because that is the what should I say? Like that is the critical point, right? Say for example, in root locus, you can easily think about it. There is always the critical gain point beyond which the trajectory or the root locus will move into the right hand side of the locus, and there in that case the closed loop system will be unstable, right? Here also, that is the, you can say it is the critical point of the parameter. Is it now fine? All of you please check yesterday's example and this one together, and then you ask me whether bifurcation is at least clear to you or not. So far we have understood or we have learned the phenomena bifurcation, but later we will learn in depth. In depth means yesterday I mentioned there are 3-4 types of bifurcations. One is transcendental, transcritical, then Hopf bifurcation, Birch-Fock bifurcation, 3-4 different types. Those things we will learn. At this moment we have learned what is the bifurcation phenomena. Okay? Have you understood by reading what I have written?
That's for asymptotically stable equilibrium.
Here, that is the phase plane analysis, why it is required. First of all, that is one question, and what is it, right? So phase plane means it is like so far, whenever we drew a trajectory, always it was with respect to the time, right? But now, this time, that is, this is the first one, like this is the first time when we are drawing a locus which is not explicitly with respect to time, because x2 and x1 individually both of them are time functions, right? Because they are solution to the system subjected to a non-zero initial condition. And now, that is, if you plot them, that is, if you plot x2 versus x1, then it will give you a relative motion of the system, okay? Relative, yeah, exactly, that is this with the locus. That means if there is a table, suppose this is time, this is the value of x1, this is the value of x2t, and serial number 1, 2, 3, 4, so on and so forth. So suppose at t equals to 0, this is x1 0, x2 0. Then at point 0, 1 you have some value. Then suppose point 0, 2 you have some value. And ultimately, suppose you have run the simulation for 5 seconds, okay, and the step size is 0.01, then how many points will be there? 501 points, right? So here up to t equals to exactly 5. So then it will be, that is 1, 501, and then x2, 501. So in that way, now all the values, whatever you have get, if you draw a locus, x2 versus x1, that is called a phase trajectory. Okay, it is a locus which gives you the relative system motion. Compared to when you draw something like that, usually we are very much familiar with the time response, right? But they are all with respect to t. It can be whether it is y or x, but the independent variable is the time. Now this time what is happening? This phase trajectory, that means it's a locus of x2 of t versus x1 of t. Some special cases can be there when x2 equals to x1 dot, but that is not necessary. Please don't think that is x2 always needs to be equal to x1 dot. That is not. If you have a system already expressed in a controllable canonical form or observable canonical form, then automatically x2 will be x1 dot. But it is not necessary that is always it has to be the derivative of the first state. Okay? Only one limitation, that is it is restricted to up to second order systems only. Okay? Once again, there is its limitation is that it is restricted only up to second order.
Sir?
Yes. And then, so that is the reason, that is what I just said, that is it is not at all necessary that x2 will be the dot of x1. That is the reason why I put them separately. Otherwise I could have written that is x1 dot equals to x2 and then x2 dot equals to function of f1 x2. I didn't write that. Have you understood what did I say?
So the trajectory with respect to relative motion of the time or relative motion of the other state?
Relative motion of the states, right? That is x2 versus x1 means now what will be the relative motion of the system with respect to x1? That is, okay. It will be clear once we take some examples. That is, what did I say? That is, you see, I could have written x1 dot equals to x2 and then x2 dot equals to f of x1 comma x2. If this is the representation, then it is compulsory that x2 is the x1 dot. then in that case, the phase plane, what we will draw, simply we can write that is x1 dot versus x1. But that is not at all compulsory. So you can easily split that into like two separate functions, f1 and f2. Both of them, the argument is x1 comma x2. If you have the representation like controllable canonical form or observable canonical form, then by default you will have that relation. That is, one of the state is a first derivative of the other. So automatically that will come. But it is once again it is not at all necessary. Okay. You can ask that is then what will be the situation for first order system? Then for first order we have only one state x. Then to calculate x dot, because like suppose you have a system that is x dot equals to minus of x, or even that is supposed to make it non-linear minus x square, and then you draw. So phase trajectory is like sometimes we think that it is a very difficult thing. So no, ultimately it's a locus. Because we learned drawing locus when? In our school days, right? Maybe in class 9, 10, then later also. That is, here it is like a locus. When you run the simulation, there are different instant of time. What is the value of x1 and x2? You just tabulate it. In fact, if you do it in MATLAB, automatically in the workspace, that data, matrix data would be populated. You double click it and then you check, you will get this table. And from that, you use the plot command to plot the trajectory. Then automatically you can see this one. Or if you use simulate, then we have a like special type of scope is there, which is called XY graph. If you attach a XY graph, you will be seeing this one. Okay.
Sir, can you please repeat that point? You have told that x2 equals to not always x2 equals to not always x1. So I didn't get that point actually.
That means that is you can have that is different. Say for example, if you have a system which is represented in the diagonal format, okay, are you getting what I am saying? Diagonal canonical form. Then would you say that is the states are, some of the states are derivative of the other? Not, right? That is the case. That's why I have mentioned that is if it is like if the system is already represented in CCF or OCF in case of LTI, then automatically this relationship holds. But it may happen that is no, it is represented in arbitrary format, no particular relation. Yes.
So when are we going with the idea of phase plots? Can we directly not go for x by t plot if we go for normal linear systems? Because if the system is stable,
right, that is the reason. That is why do you need phase plot, exactly. If we handle linear time invariant system, for them the closed form solution exists. We even know the formula e to the power at x0. From that, what you are expecting, that is this solution, like time trajectory, we can see that, and then that is whether it decays or whether it's sustained oscillation or growing. From that we can comment on the stability. But now this is highly useful for nonlinear systems, because many times many times I said that is not that all nonlinear systems will give you closed form solution, and even if the closed form solution exists, then what happens that is it will be really difficult for us to find out to solve the nonlinear differential equation, right? If you say that is, sir, I have software, I have MATLAB, and then I will check from that, that is fine. But still, it is not guaranteed that is whether for all type of nonlinear system, you will get a smooth response and which will exist for all the time interval. What is the requirement of that point? That is this, you think about that finite escape time. That is this x dot equals to minus x square. If I consider x0 equals to minus 1, that gave us the finite escape time, right? So then what was the solution? X of t equals to 1 by t minus 1. Suppose like you are thinking about that from the time trajectory, we will analyze the stability. And the moment you run it, whether it is by MATLAB script or Simulink, what will happen? Immediately the system will throw an exception or an error. Immediately the simulation will stop. Starting from t equals to 0, that is the moment it becomes t equals to 1, immediately the simulation will break.
So, but in phase portrait also we are technically finding xt of t and x1 of t, which are dependent on time. So that should happen here as well, right?
No, there, that is what do you do? That is in the, we will analyze the stability. That is, it is not that we are going to run it. It is completely for the analysis purpose. That is, we will analyze the stability of the system in the neighborhood of the equilibrium point. And then before that, the existence and the uniqueness, that we will have to check. That is this kind of situation. That is the finite escape time. That means the solution doesn't exist. Do you remember? And maybe car. Please always keep your phone in the vibrator mode, or better stop it. You see, my phone is completely switched off when I am in the class. See, in this case, that is, if you remember in the second class, I said that is uniqueness and existence of the differential equation. Like once again, if we have like LTI systems, and for them, like ordinary differential equation, constant coefficient, for them the solution exists. That is, the x of t equals to e to the power at x0, right? But the moment we step into nonlinear system, then uniqueness and existence is a big question. Say for example here. That is, if you see that is this fx, that is fx this one, and then that is sometimes if you check that is what is its derivative to find out whether it is continuous or not. Is first derivative, it is continuous. So this function, there is no problem in the continuity, right? Minus x square, this function, it is continuous, no problem in the continuity. Still you see the solution is doesn't exist for all t greater than equals to 0. So that's why that is for nonlinear system analysis. First you will have to think about the uniqueness and existence of the system. Once that is done, because once you are guaranteed that yes, the solution will at least exist for all t greater than equals to 0, then you find out the equilibrium points and then you check the stability properties of each of those equilibrium points. So there we need the phase spring analysis, like what he asked, that is what is the requirement of the phase spring analysis. We will learn the phase spring analysis on the basis of linear time invariant system, and then we will extend that for analysis of nonlinear systems. Then the question is that for like so far we have learned all like linear time invariant system, their stability analysis, all of them are well defined. Like what are the stability analysis tools we learned? Starting from like Rauthaus, like first of all, if we talk about the open loop stability, you simply check whether a transfer function has always pole on the open left half or not. If it is so, then asymptotically stable. If you have some of the at least one pole on the right half, it is unstable. If you have like one or more poles on the j omega axis, then it is marginally stable, right? But if it is nonlinear, we don't have the transfer function. Not even, that is, we have x dot equals to ax plus bu format. How would you analyze stability? That is the main difference, right? That is, as long as we handle API system, then we have both transfer function approach as well as state space approach. That is, if you have the state space, especially h dot equals to ax plus bu, you directly check the eigenvalues of the A matrix, right? From that, stability properties would be entirely clear to us. And if somebody is more comfortable with the time response, then you check the impulse response of the system, that or like the response of the system subjected to a non-zero initial condition, and then you see whether the response decays or not, then everything is fine. But in nonlinear system, what happened? That is, first of all, even if we assume that the solution will exist for all t greater than equals to 0, but still, that is, we may not guarantee the stability of the overall system, because it heavily depends upon the zone of the initial condition. Like in case of a linear time invariant system, if somebody like observe this kind of response, suppose it can be an impulse response, or it can also be like, suppose starting from a non-zero initial condition, it can be like this. And if we get this kind of response, then we are more than happy. Because why? That is the main property of the linear time invariant system, that is nature of response doesn't depend upon the initial value, I mean the initial condition. So whatever may be the x0, this pattern will always be there. So that's why analyzing linear time invariant system is really very easy. But then in case of nonlinear system, suppose then what happens, that is, if the stability property it heavily depends upon the initial condition, and then the choice of initial condition is infinite. For how many initial conditions you will be checking the time response? That is the reason, that is why you have to analyze that we need some other tools by which we can analyze the stability of a nonlinear system. Certainly not through the time domain analysis, because if you have to conclude from time domain analysis, then you have to simulate it for maybe 100 times, 200 times, for whatever different variety of initial condition you think about, then you have to do that. So that is the reason, that is why we need to have some tools for stability analysis. And what is that? One of them is phase plane analysis. Although this is restricted to second order system, but still that is, it gives us a visual representation, and also that is to start with nonlinear system analysis, it helps us a lot. Okay. And what does it say about, once again, about the stability analysis? Like suppose you have already understood that is many of the nonlinear system will have multiple isolated equilibrium points, right? So far we have not checked the continuum equilibrium point, that too we will come later, but at this moment, to keep the thing simple, we are talking about only about multiple isolated equilibrium points. So if a system has suppose 3 or 4 isolated equilibrium points, then you have to check the stability of each of those equilibrium points. Now what does it mean? That is, when I say that is, you have to check the stability property of all those equilibrium points. What does it mean? That is, you have to check, or you have to find the region of attraction for each of those equilibrium points. Immediately the question will, although you know, but still that is, you may want to listen once more, that is why the zone of initial condition is that important, which I am calling, or rather which is called the region of attraction or the domain of attraction. Because of that requirement, that is, if the norm of x0 less than delta, then the norm of xt will be less than epsilon for all t greater than equals to 0. That is the relation. Once again, I am writing for you, x naught less than delta will imply there exists a delta greater than 0, such that this will imply the norm of xt, 2 norm, will be less than epsilon for all t greater than equals to 0. Now this delta, that means there is a small circle, there is a larger circle. So the small circle is the delta, the larger circle is the epsilon, and this is called my region of attraction or the domain of attraction. We are always like bothered about this delta radius, that means that zone of the initial condition. Because if your initial condition doesn't belong to one particular delta, suppose if it is in another delta ball or different place, then the stability property may change, like the things which we discussed in case of simple pendulum. So that's why when you have multiple equilibrium point, you have to find out the region of attraction for each of those equilibrium point, and that is called the stability analysis of a nonlinear system. Okay, and this we will do with the help of phase plane analysis. That means phase plane analysis means around in the neighborhood of equilibrium point, how does the system motion go? That is, from that information we can extract from phase plane analysis. Once again, what is the relative motion of the system, or rather what is the relative motion of one state with respect to other in the vicinity of the equilibrium point? That analysis is called phase plane analysis, or rather from that we can comment about the stability. You can say that, sir, can you please explain that in a very simple word? In the simplest word, stability means this phase trajectory will somehow converge to the equilibrium point. That is the nature called stable. Or if it diverges, then it is unstable. Now, that is when it is a nonlinear system, or rather in this analysis, it is not only about stable, unstable or marginally stable. There are other classifications as well. That is, even other classification means here you must read stable means asymptotically stable, Unstable means growing, that is fine. We don't have any other category of unstable. Purely sustained oscillation means that is what we call, that is a marginal stability. But in case of ATI systems, in the category of marginal stability, there are many cases. What are the cases?
Limit cycle.
No, I haven't yet started limit cycle. Did you say limit cycle? Limit cycle, yes, that is of another phenomena. At this moment, I am not introducing that, okay? Although we have a preliminary knowledge of limit cycle, of course. So, what are the conditions? That is, what is the stability? Then, first of all, asymptotically stable. Then, marginally stable. Unstable. Earlier, we knew these three broad classifications, right? Now, this marginal stable, here we have few subclasses. Can you tell me why? One is the case like if you have a single pole at the origin, that is one particular category, suppose 1 by S. Okay. Then another case is that purely sinusoidal case. Suppose you have 1 by S square plus 1. Right. And here another one will be there, I will come later. Even in asymptotically stable, there can also be cases like, suppose 1 by S plus 1, that is fine, asymptotically stable. What will be the nature if it is repeated 1 by S plus 1 whole square? No, that would be definitely stable, but in the, if you have to draw that face plane, how that locus will look like. So these cases actually we treat in a separate way. So what did I say? That is, earlier we had only three broad classifications: asymptotically stable, marginally stable, unstable. But now we are analyzing even further. That means we are further drilling down. That is, within the marginal stability cases, there can be different types. Like 1 by S, that is 1 by S square. I am not taking that one because 1 by S square anyway it will be unstable. But 1 by S square plus 1 purely sinusoidal, that is the sustained oscillation kind of thing, right? So, the advantage of phase plane analysis is that is you will find that is all these different type of cases will give you a different type of locus. From that we can easily conclude the type of the stability. Even in the unstable cases also something like that, if you have 1 by S minus 1 into S minus 2, definitely it is unstable. But there can be another little favorable category like 1 by S plus 1 into 1 by S minus 1, like the transfer function of an all-pass filter. Sorry, not the symmetric poles. Plus 1, this is minus 1. This kind of system, although theoretically unstable, but still that is they are possible to handle in a good way. By mistake I said all-pass filter. All-pass filter means the transfer function is 1 minus S by 1 plus S, where actually you have a symmetric pole 0. This one means symmetric poles, but all-pass filter means there is symmetric pole 0. Okay.
What about that 1 by square?
1 by S square, that is unstable.
So, why do you write it under the unstable category?
That is, you can say about that is this shouldn't be there. It shouldn't be there means it is also a category, but actually this is not marginally stable. So that's why sometimes that is we tend to think that is 1 by S square is also marginally stable, but 1 by S square, any repeated poles on the j omega axis is not marginally stable. That is unstable, right? Whether this is 1 by S square or even like 1 by S square plus 1 whole square, the moment you accept repeated poles, it will be unstable. So in phase plane analysis, all these separate cases we will handle separately. Okay. One is the case of real eigenvalues, okay? Another one is the case of complex conjugate eigenvalues, okay? These two can be the broader classifications after diagonalization. So here, what other things can happen? That is about x1 greater, sorry, lambda 1 greater than lambda 2. This can be one possibility. Lambda 2 less than, sorry, lambda 1 less than lambda 2. That can also be a possibility. Then lambda 1 equals to lambda 2 equals to lambda. That can also be a possibility, right?
Lambda 1 equals lambda 2, then there should be a 1, right? Instead of 0. Then it becomes as a Jordan mechanical form.
If it is so, you are right. If it is so, then definitely. But you are missing one case. That is, if it is M equals to GM, that can also happen, right? Have you understood what he has asked? A really important question. That is, if it is repeated eigenvalue, lambda lambda, then it can easily happen that here, that is, you have a 1. Yes, that can happen. But what I consider, that is the situation M equals to G. And there it is a complex conjugate. I mean, here the lambda 1, 2, that will be alpha plus minus G beta. Here about now that for different type of eigenvalues, although broadly these two are the structure of the A matrix, then we'll have to find out that is how those locus or loci will look like. That is, for each of these different eigenvalue combinations, how does the x2 versus x1 locus will look like? That we'll have to find. Okay, so there you might have heard some of the names like stable node, unstable node, saddle point, like the stable focus, unstable focus. All those things we will learn one by one. Okay.
So are lambda 1, lambda 2 negative or positive?
Here at least see if the system, if it is already unstable, like suppose you have a nonlinear system, and then after applying the Jacobi linearization, that means after linearizing with respect to an equilibrium point, if the A matrix has at least one eigenvalue on the open right hand side, immediately you can conclude that this is unstable. So that's why here our entirely analysis is that when the eigenvalues are there on the left hand side, whether repeated or non-repeated, also on the J omega axis, and maximum we can allow one eigenvalue on the right hand side.
That means you are not giving any restriction to the eigenvalues.
That is here, that is at this moment what should I take written? That is both lambda 1, lambda 2, they less than 0. Okay. Sometimes that is they can, if they are, then the another classification will be that is like one of them is 0. That is, then this is case 1 suppose, then one will happen that is lambda 1 less than 0, but lambda 2 equals to 0, that is case 2. Then case 3, lambda 1 equals to 0, but lambda 2 less than 0. Okay? So what I can write, this is case 1, this is case 2, this is case 3. When you are taking notes, all of you please make sure that is the questions answer, like the queries which I am answering, you also note it down and you keep it as a note, because those things are actually main interesting learning.
So then it should be minus alpha, lambda 1, 2.
Yes, but at this moment here I didn't specify whether they are positive values, but if you consider both of them to be positive, then yes, of course we can write about minus lambda. Okay, sorry, minus alpha. So these two are the main classification and the pattern. So this is one pattern, this is one pattern. So here real eigenvalues, this is complex conjugate eigenvalues. Among that also we can have like many cases. First of all, like suppose when there is lambda 1, lambda 2, both are negative. if in that lambda 1, lambda 2 both are negative, then it can happen lambda 1 is greater than lambda 2 or lambda 1 is less than lambda 2 or even both of them are same. Again it can happen case 2 where lambda 1 negative but lambda 2 0. Case 3 lambda 1 0 but lambda 2 negative, and then case 4 lambda 1 less than 0 but lambda 2 greater than 0. Actually this is the case which will later learn saddle point. I said there is here in this analysis some of the extra information we will be gathering. It is not that only asymptotically stable, marginally stable and unstable, right? So here in this, through this analysis we will learn something more. So that's why you can see that is here we are considering one eigenvalue at the right hand side. That is, before that we always discard it. That is, the moment you find one of them in the right hand side, then we think that it is a gone case. Okay, but no, here we will find that is okay. If it happens, that is like that is the case of the simple pendulum. Suppose one of the equilibrium point is asymptotically stable. So suppose it gives you what is that called? Inward spiral. What is that called? Stable focus. Stable focus. And another one in the vicinity, suppose if it is a saddle point, then you have to operate the system so that it always lies within the region of attraction. So what did I say? That is, suppose you have a nonlinear system having multiple equilibrium points. One is stable, some other are quasi-stable or unstable. Then you have to design the controller so that it always keeps the system operating within the region of attraction of the stable equilibrium point. Because if it goes beyond that zone, then what will happen? Immediately that would be attracted towards the unstable equilibrium point. That's why the stability analysis of all the equilibrium points is really very important, because you have to design the controller so that it keeps the system within the zone of like initial condition of the stable equilibrium point. Okay?
Sir, for LTI system, when we design controller, so first we check controllability. Okay. So if system is controllable, then we can design controller. But if system is partially controllable, that's when if it's stabilizable, then also we can design the controller. For non-linear system, when we can stand our hand that we cannot design the controller.
There are many situations. Say for example, like first of all you have to check whether the system is well behaved or not. If it happens something like that, then it is really a difficult thing. Then for that you have to consider a nonlinear state feedback, and then you have to remove this kind of nonlinearity. So in case of linear system, really a very rare cases we surrender, but there are many types of nonlinear system that is for which we will be really fall in trouble. I will give you an example. That is, at this moment I am not taking that complicated ones.
So then what's the solution?
Sorry?
There's no solution there in that case.
No, that is, there also in some cases there are not solution, but in some cases what we do, we add feed-forward control. Feed-forward, although that is a restrictive type of control, but in some cases actually there is no other way out. Then we apply feed-forward control. In that way we manage, or else we apply gain scheduling. That is, like for each of the segment we apply one controller, then in another segment you tune the gain. In that way we apply. Instead of x bar, I am writing z, and also that will help you to match with the book. Suppose z dot equals to a bar z, where z is the new state. And now z also belongs to R2, z1, z2. Okay. So if this is the situation, then what will be your solution of z? z1 equals to e to the power lambda 1t. At this moment I am not writing minus. Okay, let's see what happens. Lambda 1t. and then z, sorry, not z1 comma 0, the initial condition, because now it is in the diagonal form, we can easily write down the solution, right? And then your z2, what will be that? That is e to the power lambda 2t z2 0. So they will be the solutions of the system in the change coordinate, I mean in the diagonal coordinate. Now we need a, like, ultimately what is the phase plane trajectory? That's a locus z2 versus z1, right? So from that, can you help me to find a relation z2 equals to something into z1? Can you find that out? You will find there will be a constant term that will be z20 divided by z10 to the power something and something e to the power term. Can you find that out? Let's take a small break. ब्रेक लेते लेते तुम लोग सोचो मोमेंटरी। हाँ हाँ, आज हम लोग पूरा एक्सटेंड करेंगे 9 बजे तक। এটা কি একটু গাড়ি বন্ধ করে দাও ততক্ষণের জন্য। হ্যাঁ